I'm Jacob Konikoff, and today I'm going to be going over this do file, which was referenced in our call last week, though we didn't really have a chance to get to it. I really appreciate that at least some of you looked at the do file on your own after the call, and the feedback I got actually led me to add in a lot more commentary into the do file, as well as change some of the setup of the do file to allow for more relevant and complex analyses. So this do file starts off the way the other do files we've talked about usually do, with the two commands clear and set more off, just to wipe everything out of Stata and make it so Stata will print all of our results. I've added here a bunch of commentary about how you might change this do file if you were to look at variables that focused on different levels of the data. So this do file is going to be about the variable ANC42, which is antenatal care, and it's a variable at the level of a woman. So we're looking at the antenatal care that woman is receiving, but we know that some of the variables in DHS are at the level of children, the children of these women, and some of them are at the household level. For example, insecticide-treated nets. So you're going to have to modify this code depending on what level of variable you're dealing with, largely because there's going to be different types of nesting going on. So with a variable like ANC42, which focuses on women, we're looking at women nested within households, nested within enumeration areas, and that will change. For instance, if we're looking at a child level variable, we'll want to nest children within women. So the next command we've got here is use and then the file path where the data has been stored. So you're going to have to change that on your machine. For example, this is what Lois put when she was helping me out to create this do file. The next thing we're going to do is we want to take into account the stratification of the sampling. To do that, I'm going to generate 11 new variables, which will just indicate which strata each sample was taken within. So the 11 strata are the 5 different regions, which have been divided into urban and rural, as well as the capital, Bamako, which is entirely urban. And I'm going to use this tab v023, comma, generate strata, and that's going to make 11 new variables called strata 1, 2, 3, etc. And you can see here which of the different regions and the urban-rural divide each strata references. So that's outputted here in Stata when I type this tab command. The next thing we're going to do is we're going to generate the weights we're going to be using for this analysis. So the first thing we need to do is create a new variable, which I called SumEA, stands for the sum of the enumeration areas, because I'm going to sum up all the weights in each of the enumeration areas. So V005 is the weights assigned to each individual. You have to scale that by 10 to the 6. And if you add those up, it will give me the total weight for each enumeration area. That's what I'm going to use at the highest level of clustering here. So remember, we have women within households within enumeration areas. So I'm going to use that sum of weights to weight my sampling at the highest level. At the lower two levels, which I call weight 2 and weight 1, what I'm going to do is I'm going to assume that once I've sampled an enumeration area, which I know happens with unequal probability, that women and households are sampled within those enumeration areas with equal probability. I'm going to do that by just setting the weights equal to 1. For this type of analysis, you're going to have to call your weights weight 1, 2, 3. If you had a fourth level, you need to call it weight 4. And the lowest level, so for example, if we had children, has to be weight 1. The next level up has to be weight 2, and the highest level is always going to be the highest number. Now that we've got our weighting, the weights that we're going to use for this analysis, we need a couple more things before we can actually run the analysis. So the next thing I'm going to do is I'm going to create a variable, which I call women, which will denote each unique woman in the data set. I do that with this egen woman equals group case ID. I'm going to do the same thing for the households and the same thing for the enumeration areas. And we're going to use this in the GLAMM command in order to designate what the clustering structure is. Next, we have a chunk of code here which I've denoted with these long set of asterisks, which just create the ANC42 variable. And this is code I borrowed from a previous set of stata commands that you should be familiar with, so I'm going to skip over that here. Now we're ready for the meat of our analysis, which is this GLAMM command. And the way that command works is you first write the command, then the variable we're interested in, which is ANC42, and then what we're regressing that variable on. So here it's the 11 different strata. Now importantly, I've specified here no con, which stands for no constant. What that's going to do is give us the direct effect or the coverage within each of the 11 different strata. I've then specified I and then the higher levels of clustering. So you don't need to place here whatever is the lowest level. In our analysis, that's woman. But you need to place here the higher levels of clustering. So we have women within household, and then the households are within enumeration area. So if we had an analysis where we also had child, you need to write woman space household space enumeration area. The next two commands, family bin and link logit, simply deal with the type of data that we have. So we have what's called binary data, which means that either a woman met the criteria or not. It's a yes, no binary choice. It's not something continuous like height, where each woman could have her own height and those heights could range over many values. Next, we're going to take into account the fact that there is weighting. By using those weights we designated up above with the command pweight weight. And then finally, adapt is a type of method for fitting these models called adaptive quadratures, and I'm going to put that adapt command here. So if I go to my window here and I run the GLAMM command, it will show me these iterations. It's fitting the model, and then once it's done, I will get out a bunch of estimates for the strata. Now these estimates here, this first column that says coefficient, don't actually give me what I'm interested in. Those give me the log odds ratio. But what I want is the marginal predictive probabilities, which is equivalent in this scenario to the coverage rates. So to get that, I'm going to use this GLA pred command, which is similar to the predict command that you've used in the past. I'm going to label where I'm going to store those variables, prob, and then mu marg. You need to put those in order to tell me that I want the marginal probabilities, which is what we're after in this case. So that's going to output into this new variable I've created, prob, the probabilities I'm interested in, which is the coverage in each of the 11 different strata. If I want to see what those actual values are, I can type tab2 prob v023, which tells me I want a two-way table. One of the directions is going to show me the prob, these marginal probabilities I just created, and the other is going to show me the different strata, which are stored in v023. So reading this table can be a tiny bit confusing, but what you can do is you can go here, you can find a probability, and then you just go over until you find which of the regions does not have a 0 for that probability. So here it's over here. So that means that MOPD rural is the strata that has a coverage of 16%. I'll do another example here just so we're clear. If I wanted to know what percent we had of coverage in K's urban, I'd find that this is the non-zero there, so it's 56%. Okay, so now what we really want is the regional coverage. We don't want the coverage by strata. Now we had to incorporate the strata into our model in order to deal with the fact that the sampling was conducted in a stratified manner. Now, to get out that coverage, I'm going to take you through a few different things. The first thing I want to bring up is in the old do file, there was a command that allowed you to just get out the confidence intervals for these probabilities. So I don't know if you remember, but we made this wonderful little graph, and we got those confidence intervals through the following command, which I'll pull up here, which I've commented out, so it might be a tiny bit hard for me to find, but it's this ci marg mu marg p underscore cil marg p ciu level 95 reps 1,000 dots. Okay, so this command gives out the lower and upper bounds of the interval for the marginal probabilities, the coverage probabilities, and it stores them in the lower ones in this marg p cil. You can actually write anything here. It's just defining a new variable that will have this name. And marg p ciu, again, you can label that anything you want. This level here means that I want 95% confidence intervals, as opposed to, say, 90% confidence intervals. And then reps is actually telling me the number of bootstraps iterations I'm going to do in order to generate these confidence intervals. Now, before we continue, I'm going to talk very briefly about what a bootstrap is. It essentially is a method for generating hypothetical samples from the population. We need these hypothetical samples from the population because they'll tell us something about the uncertainty in the sample we did get from the population. So we have one sample. We have the DHS 2012 Molly sample. But if we could have 1,000 samples from the population, hypothetically, then we would know a lot more about where the truth is, what the true coverage rates are in the different regions. So the bootstrap statistically creates sort of 1,000 different hypothetical samples, and we're going to use that in order to learn a lot of different things about those coverage probabilities. So the first thing is we could do a command like this, which generated out these confidence intervals, and we started to discuss how even though ultimately we're interested in the regions, it's interesting to notice that the rural values are always significantly lower than the urban values. So that tells us something about what might be causing different discrepancies within the population. So I'm not going to use this command. Instead, what I'm actually going to do is I took out the sort of guts of that command and I made it so that we could run it here, starting with this meta. But instead of it just giving us out the final answer at the end, where the upper and lower bounds of the confidence intervals are, when we run this command, and this is going to take quite a long time, it's going to start printing out each repetition just because it takes about 2 hours to run. So you can follow through as it runs through the repetitions. You'll know how far you've gotten. And when you're all said and done, once you make it here through that command, what you'll actually have, if you look at your data, let's try to pull that up. Oh, that's the graph. If you look at your data, you'll see that I've created 1,000 new variables here. And each of these variables are the estimated coverage probability in a new hypothetical sample from the population. So, for example, you saw that the marginal probability was about 16% in that first region we looked at. But you'll see if we hypothetically sampled again, we might get 15.5%. We might go higher. We might get 17%. Go even lower, 13.4%, etc. And now that we have all these potential probabilities, I think I saw 26% in there. So you can see there could be quite a range potentially, right? We're going to be able to use that to generate confidence intervals, not just for the probabilities of coverage in the different stratification. So not just these probabilities, but any linear combination of these items. So for example, if we wanted to know what the coverage was in MOPD, not MOPD urban and MOPD rural, what we could do is we could weight these two different probabilities by what percentage of MOPD is urban and what percentage is rural, and then we could use these bootstrap iterations here to get out a confidence interval. And I realize that this is a fairly complex and probably new idea and topic, so I'm going to conclude this video here. Or actually, I'm just going to say one more thing, which is just like I got that graph using that command, I've written a new command, which I'm going to show you how to use, which once you've finished that bootstrap, you don't have to take all that time to run the command again. It's called ci-marg bootstrap, and it will generate out the lower bounds and the upper bounds in whatever you label these two variables once you've executed this part of the code. And again, this takes a couple hours to execute, so I guess patience for now. And that will conclude this StatFram video. There's going to be a couple more to come, which will really start to delve into how to get the regional effects and how to make comparisons between different regions, as well as how to load your own commands